We wake up to alarms, count birthdays, measure journeys, and watch seconds slip away, yet no one has ever seen time itself. It is the invisible stage on which our lives unfold. But the deeper we look, the stranger it becomes. Clocks lose meaning in the void of space. At the edge of black holes, seconds stretch into centuries. Deep underground, isolated from sunrise and sunset, the mind forgets what a day even is. Some scientists now believe time might not exist at all, just change, memory, and motion woven into a story we tell ourselves. So what is this thing we call time? And if it isn't real, why does it rule everything we do? In the heart of the Atacama Desert in northern Chile, where the sun blazes so fiercely that rain has not touched the ground for decades, time begins to lose its grip. There are no clocks here, no ticking hands to remind you of passing hours. Only the endless horizon of ochre sand and salt plains stretching beyond sight. The wind carves new patterns into the dunes each day, yet there is no witness to mark when one shape ends and another begins. A fossilized tree root, buried for 10,000 years, juts from the cracked earth as if it had been placed there moments ago. Out here, the line between minutes and millennia begins to dissolve. And the question creeps in quietly. If everything changes, but nothing keeps count, does time exist at all? Beneath the ocean, where light cannot reach and the pressure could crush steel, that question deepens further. In 2012, scientists aboard the research vessel Nautilus lowered their cameras into the pitch-black depths of the Gulf of Mexico, searching for hydrothermal vents that had been spewing mineral-rich water for perhaps tens of thousands of years. They filmed ghostly white tube worms swaying gently, their colonies older than any human life, thriving without sunlight or seasons. Down there now has no meaning. The same slow chemical reactions that fed the first microbial life billions of years ago still unfold. Unhurried, unmeasured, unaware of the centuries passing above, without the ticking of a clock, without even the rise and fall of a tide, change continues. Indifferent to whether anyone calls it time, if deserts and oceans begin to erode our sense of hours and days, space obliterates it entirely. In 1977, when the Voyager 1 probe was launched from Cape Canaveral, it carried a golden record and a faint hope that one day, perhaps tens of thousands of years from now, some distant civilization might find it. Today, it drifts more than 24 billion kilometers from Earth. Beyond the influence of our sun, where there is no sunrise or sunset, no orbit to mark a year, it simply moves, inch by inch, into the void. Its radio signals take over 22 hours to reach us, and yet they arrive as if from a timeless present. Out there, time loses its familiar texture. Nothing ages, nothing hurries, nothing waits. Yet even here, in places where time seems meaningless, change never stops. The dunes still shift. The vents still breathe. The probe still drifts. The paradox is stark and unsettling. Everything we see, touch, and measure is in motion, always transforming from what it was to what it will be. And yet the thing we call time, the invisible medium in which this happens, is nowhere to be found. We can hold a clock in our hands, watch the second hand crawl around the dial. But what it measures is not a substance we can capture. We do not see time flow past us like a river, nor can we trap it in a jar and show it to a friend. We are surrounded by change and yet blind to time itself. Humans have always struggled with this contradiction. The philosopher St. Augustine, writing in the early 5th century, admitted he knew what time was until someone asked him to explain it. "What, then, is time?" he wrote. "If no one asks me, I know. If I wish to explain it, I know not." More than 15 centuries later, that confusion remains. We build atomic clocks in underground laboratories that lose only a second every 100 million years. Yet those clocks still do not reveal what time is, only how precisely we can count it. And so we keep counting. We number our days, record our birthdays, celebrate anniversaries, and mourn losses by the turning of the calendar. We map the histories of civilizations and the lifespans of stars, all measured in seconds, years, and ages. But none of this reveals the thing itself. When a rock crumbles into sand over millennia, we say, time has worn it down, but what has truly acted upon it? When a newborn becomes an old man, we speak of time passing, but we cannot point to the force that made it so. It is as if we have invented a language to describe something we can never see, a ghost that leaves only footprints. If you sit quietly in the desert's stillness, in the deep ocean's dark, or beneath the cold silence of the stars, you might begin to sense the truth. The ticking of your watch does not come from the universe, but from your wrist. The seconds it counts are nothing more than agreements humans made to keep track of change. The heartbeat you feel, the breath you draw, the hair that grays with the seasons, these are real, measurable, undeniable. But the time that supposedly carries them forward remains invisible, intangible, absent. Everything changes, yet time itself never shows its face. And perhaps that is the great mystery, that what we call time is not a thing at all, but the shadow cast by change, a clock that isn't there, keeping measure of something we still do not understand. Long before the first gears turned inside a clock, before pendulums swung in cathedral towers, and before atomic pulses defined the second, humans stood beneath the sky and wondered how to measure something they could never touch. They watched the sun rise and set, the moon wax and wane, stars shift in their nightly march. And they understood that though each day seemed the same, none was ever truly identical. Fields ripened and withered, rivers swelled and shrank, herds migrated across plains, and winter always returned. Somewhere in that repeating pattern, they sensed the presence of something invisible threading through their lives, something that ordered the chaos, guided the seasons, and determined when to sow seeds or prepare for floods. And so they began to build tools, crude and simple at first, to capture what could not be seen, believing that if they could measure the rhythm of the world, they might also master it. The earliest known attempts to measure time were born not from curiosity, but from necessity. Around 1500 BCE, Egyptian farmers placed vertical sticks into the ground, watching how their shadows moved across the sand as the sun crossed the sky. These early shadow clocks, sometimes carved from stone or wood, divided daylight into segments, helping priests schedule rituals and laborers pace their work. The Egyptians noticed that the length and angle of the shadow changed not only as the day progressed, but also as the seasons shifted. And this observation tied their daily lives to the larger cycles of nature. In the fertile Nile Valley, where the river's annual flood dictated planting and harvest, such awareness meant the difference between abundance and starvation. If they could predict the river's rise, often heralded by the appearance of the star Sirius just before dawn, they could prepare their fields and granaries. In that sense, measuring time was not just an intellectual exercise, but a survival strategy. In Mesopotamia, the Babylonians approached the same problem differently. By 1600 BCE, they were using clepsydra, or water clocks, devices that marked the passage of hours by the steady drip of water from one container to another. These clocks were used in temples and courts, where rituals and legal proceedings required precise timing, and their simplicity concealed a profound idea that time could be separated from natural cycles and measured artificially, independent of the sun or stars. This was a turning point in human thought, a moment when measurement began to drift away from observation and toward abstraction. The Babylonians, like the Egyptians, were still responding to the needs of their environment, predicting floods, charting the seasons, regulating civic life, but they were also beginning to believe that time could be contained, that it might exist within a vessel just as water did. The Greeks later refined this thinking. In the 3rd century BCE, engineers such as Ctesibius of Alexandria created more sophisticated water clocks with gears and dials, even incorporating miniature figures that moved as time passed. These were no longer mere tools for agriculture or worship. They were mechanical representations of something deeply mysterious. Time, once tied to the stars and rivers, was now something that could be manufactured, displayed, and shared. People began to arrange their lives not around the unpredictable flow of nature, but around regular intervals measured by devices they had built themselves. Yet as these inventions grew more precise, A subtle shift occurred in how humans understood the world around them. What had started as a way to track natural rhythms gradually became a belief that the measurements themselves were reality. A farmer planting barley near the Nile in 1300 BCE might look to the rising of Sirius and the changing length of shadows to know when to till the soil. But his descendants, centuries later, would look to a clepsydra or sundial and trust the markings on its surface more than the feel of the earth beneath their feet. Measurement, once a tool, became a master. This transformation can still be seen in surviving artifacts. In 150 BCE, Roman craftsmen carved portable sundials small enough to carry on journeys, inscribed with city names and latitudes so travelers could keep track of the hours far from home. These devices were not merely conveniences. They symbolized a new belief that time was a universal quantity that could be divided and possessed. A Roman senator could now say he met a colleague at the third hour and expect him to understand exactly when that was, no matter where they stood. In creating a shared language of time, humanity also created an illusion that time was not just a human perception of change, but a thing that existed independently of the sun, the seasons, or the pulse of life itself. This illusion grew stronger over centuries. Calendars carved into stone or written on papyrus, from the Babylonian lunar calendar to the Egyptian civil calendar of 365 days, attempted to bind time into units of days, months, and years. Each revision brought more precision. But each step also distanced humanity further from the natural flows that had inspired those systems in the first place. The ancient Chinese recorded eclipses as omens. The Maya tracked celestial cycles with astonishing accuracy, and priests in Thebes timed their prayers to the rising sun. All believed they were measuring time itself. Yet they were always measuring change, the Earth's turning, the moon's orbit, the tilt of the seasons, not the unseen current that might lie beneath it. By the time Julius Caesar reformed the Roman calendar in 46 BCE, adding leap years and aligning the months with the solar year, the shift was complete. Time had become not just a tool for survival, but a structure for society. Markets opened and closed at specific hours. Festivals followed predictable dates. And empires synchronized their armies and laws to the ticking of a human-made schedule. People no longer asked whether time existed beyond their measurements. They accepted the markings on their sundials and the dripping of their water clocks as proof that it did. Yet even then, as shadows stretched across marble forums and water flowed through bronze clepsydrae, the same paradox lingered as it does today. Everything changed. Crops grew, stars moved, people aged, but time itself remained hidden. What our ancestors built to understand the invisible became the very thing that blinded them to its mystery. And in mistaking the measurement for the reality, they turned a human invention into the heartbeat of the universe. In the spring of 1583, inside the cool stone walls of the Cathedral of Pisa, a young student named Galileo Galilei stood beneath the vast dome and waited for a lecture to begin. The air was heavy with the smell of candle wax and incense, and the murmur of prayers still echoed in the arches above. As his eyes wandered across the dim interior, he noticed a bronze lamp hanging from a long chain high above the nave. A breeze, or perhaps a careless hand, had set it in motion, and it now swung gently back and forth. At first, there was nothing remarkable about the sight. Such lamps were everywhere in Italian churches, but something about its motion caught Galileo's attention. As he watched it sway, he felt the pulse in his wrist and began to compare the two rhythms. And to his astonishment, the swing of the lamp remained steady and unchanging, even as its arc grew shorter and slower. It was a small, almost invisible moment, yet it would become one of the most significant observations in the history of science. Galileo was barely 19 at the time, still more interested in medicine than mathematics, but the image of that lamp followed him for years. He would later recreate the experiment using pendulums he built himself. And he confirmed again and again that their period, the time it took for each swing, remained constant. Regardless of how wide the swing was, as long as the length of the string stayed the same. This principle, called isochronism, might seem simple now, but in the late 16th century, it was a revelation. Timekeeping devices of the era were crude and unreliable. Sundials were useless on cloudy days, water clocks were inconsistent, and early mechanical clocks drifted wildly, losing or gaining hours in a single day. Galileo's observation suggested that nature itself offered a far more precise and dependable metronome than anything humans had yet built. As Galileo's reputation grew, so did the importance of his discovery. By the early 17th century, the expanding world of navigation and trade demanded a new level of precision. European ships were crossing oceans in search of spices, gold, and new territories. But without accurate timekeeping, they struggled to determine their position at sea. Latitude could be calculated by the stars, but longitude, the east-west position, required knowing the exact time difference between the ship and a fixed location back home. Even a small error could send a vessel hundreds of miles off course, costing lives, fortunes, and sometimes entire fleets. Galileo understood that a pendulum clock, with its steady, reliable rhythm, could be the solution, and in 1641, a year before his death, he sketched the design for such a device, complete with a pendulum-driven escapement that would regulate its motion with unprecedented accuracy. Although Galileo never built his clock, his ideas did not vanish with him. In 1656, a Dutch scientist named Christiaan Huygens took Galileo's concept and turned it into reality. Huygens' pendulum clock was astonishingly precise for its time, losing less than a minute per day, a dramatic improvement over the clumsy mechanisms that came before. Within a few decades, the best pendulum clocks were accurate to within seconds. This leap in precision was more than a technical achievement. It reshaped how people understood and used time. Churches could ring their bells with perfect regularity. Merchants could schedule departures and deliveries, and astronomers could record celestial events with a consistency that allowed them to refine their models of the cosmos. But perhaps nowhere did the pendulum's influence reach further than in navigation and empire. As maritime nations like Spain, Portugal, and England competed for control of trade routes and colonies, the ability to measure time precisely became a matter of geopolitical power. Accurate clocks allowed navigators to chart courses across the Atlantic with confidence, shortening voyages and reducing losses. Naval fleets could coordinate attacks down to the minute, striking enemies with a precision that had once been impossible. Even the rise and fall of great trading companies, such as the Dutch East India Company in the 17th century, depended on a mastery of time that pendulum clocks helped make possible. Time had always been present, but now it could be captured, measured, and wielded. The shift was profound and irreversible. What had begun as a curious observation in a quiet cathedral, a lamp swinging above a distracted student's head, had evolved into a tool that could shape empires and decide wars. Rulers soon understood that whoever controlled time controlled the rhythms of daily life, the pace of commerce, the schedules of armies, and even the heartbeat of their nations. Town squares across Europe began to fill with clock towers, their bells dividing the day into equal parts and reminding citizens that time now belonged not just to the heavens, but to human hands. Galileo could not have known, as he stared upward at that gently swaying lamp, that his moment of curiosity would ripple outward across centuries. Yet the principle he uncovered transformed more than just the science of timekeeping. It transformed the fabric of society itself. By the 18th century, the pendulum was no longer simply a scientific tool. It was a symbol of order, discipline, and power. The rhythm that once ticked quietly in Galileo's wrist had become the rhythm of the modern world, governing factories, armies, and empires alike. And so, from a single moment in a cathedral in Pisa, humanity's relationship with time shifted forever from a mystery observed to a force controlled, a tool of survival to a weapon of dominance, a shadow we once chased into a mechanism that shaped the course of history. In the middle of the 18th century, as ships from Britain, Spain, France, and the Netherlands pushed deeper into the vastness of the world's oceans, the sea remained a realm of both extraordinary opportunity and terrifying uncertainty. Nations competed fiercely to establish colonies, expand trade networks, and project military power across the globe. Yet even the most seasoned navigators shared a single, maddening weakness: they could not accurately determine their longitude. Latitude, the measure of how far north or south a ship was from the equator, could be calculated with relative ease by observing the angle of the sun at noon or the height of the North Star at night. Longitude, however, the measure of how far east or west one was from a fixed point, usually the Greenwich meridian, depended on knowing the precise time difference between the ship's location and a reference point back home. Without that knowledge, a ship could be hundreds of miles off course and never realize it until it was smashed against a reef or missed its destination entirely. The consequences of this ignorance were often catastrophic. In October 1707, a British fleet under Admiral Sir Cloudesley Shovel misjudged its position while returning from Gibraltar and wrecked on the Scilly Isles near Cornwall, resulting in the deaths of more than 1,400 sailors. It was one of the worst maritime disasters in British history, and a stark reminder that, despite centuries of exploration, the oceans remained treacherous. Even in less dramatic cases, the inability to calculate longitude caused costly delays, lost cargo, and bitter defeats in naval battles where timing and position were everything. The great powers of Europe understood that solving this longitude problem is more than a scientific curiosity. It was a key to global dominance. In 1714, the British Parliament offered a staggering prize, £20,000, equivalent to millions today, to anyone who could devise a method to determine longitude at sea within half a degree of accuracy. Astronomers, mathematicians, and inventors rushed to claim the reward. The Royal Observatory at Greenwich became a hub of theoretical work, where scientists like Edmund Halley and Neville Maskelyne argued that the answer lay in the stars. They believed that careful observations of the moon's position against the background of constellations, combined with complex tables of celestial motion, could provide a celestial clock to calculate longitude. Their approach was elegant in theory but maddeningly impractical on the heaving deck of a ship. Where telescopes shook and clouds obscured the sky, into this world of academic prestige and mathematical abstraction stepped an unlikely figure: John Harrison. A self-taught English carpenter and clockmaker born in 1693 in the small village of Falby, Harrison was not a scholar or a member of the scientific elite, but he was driven by an obsession with precision and a deep belief that the solution to the longitude problem lay not in the heavens, but in the regular beating of a clock. The challenge was formidable. Mechanical clocks of the era were delicate and unreliable, their pendulums disrupted by the motion of the sea and their mechanisms warped by changes in temperature and humidity. Yet Harrison spent decades refining his designs, building a series of increasingly sophisticated sea clocks, each more accurate and durable than the last. His early attempts, known as H1, H2, and H3, were ingenious but flawed. They used balances and counterweights instead of pendulums, and they incorporated materials designed to compensate for temperature changes. But none achieved the level of precision required. Harrison refused to give up. By 1759, after more than 30 years of relentless experimentation, he unveiled H4, a remarkable marine chronometer that resembled a large pocket watch more than a ship's clock. H4 was revolutionary not only in its compact size, but also in its accuracy. In 1761, it was tested on a voyage to Jamaica aboard the HMS Deptford, and performed almost flawlessly, losing only about 5 seconds over 81 days, a margin of error that is translated to fewer than 2 nautical miles. Harrison's triumph was not immediately celebrated. The scientific establishment, particularly Maskelyne and the Board of Longitude, resisted awarding him the full prize, partly because they favored the lunar method, and partly because they could not believe a common clockmaker had solved a problem that had confounded scholars for centuries. Harrison spent years petitioning Parliament and the king, and it was not until 1773, when he was nearly 80, that he received a substantial portion of the reward. Yet by then, the impact of his invention was undeniable. The marine chronometer became an essential tool aboard ships, allowing navigators to fix their positions with unprecedented accuracy. Trade routes grew safer and more efficient, Voyages became faster and more reliable, and the ability to project naval power across vast distances increased dramatically. The consequences of this technological leap rippled across the world. With reliable longitude, the British Empire expanded its reach, establishing far-flung colonies and dominating global commerce. Naval supremacy, which depended on precise timing and coordination, became the cornerstone of imperial strategy. Even rival powers such as France and Spain adopted marine chronometers. Recognizing that mastery of time was now as crucial as mastery of wind or cannon, the oceans, once unpredictable and perilous, became highways of empire, mapped, measured, and controlled through the steady heartbeat of Harrison's invention. The story of the longitude problem is not merely a tale of scientific progress. It is a story of how time itself became a weapon of power. By turning the invisible into something measurable, by taming its stubborn refusal to reveal itself, humanity gained control over space, trade, and war. A fleet could now arrive at the precise hour to blockade a port or intercept a convoy. Merchants could synchronize their departures to exploit seasonal winds in markets. Explorers could map coastlines and chart new worlds with confidence. And at the center of it all was the relentless tick of a clock, a mechanical echo of Galileo's swinging lamp, refined over centuries into the heartbeat of empire. Time, once a passive backdrop to human endeavor, had become its most potent tool. Whoever could measure it accurately could shape the future itself. In the early decades of the 19th century, before the scream of steam whistles and the blur of iron wheels changed the rhythm of daily life, time was still a deeply local thing. Every town, no matter how small or remote, set its clocks by the position of the sun, so that when the church bell struck noon in Bristol, it might already be 12 minutes past noon in London. And when a shopkeeper in York closed his doors at 5, the streets of Liverpool were still 4 minutes shy of that same hour. These differences seemed trivial in a world where travel was slow and communication even slower, where a journey between towns took days by horse and carriage, and no one thought to question why their neighbor's time was slightly ahead or behind. For centuries, this patchwork of local solar time suited a society that moved at the pace of footsteps, sails, and seasons. But with the arrival of the railways, the old order began to unravel. When George Stephenson's pioneering locomotive, the Rocket, first raced along the tracks near Rainhill in 1829, it was not just a demonstration of engineering brilliance, but a preview of a world about to be compressed and reordered by speed. As the network of rail lines spread across Britain in the 1830s and 1840s, trains began connecting towns in hours rather than days, and for the first time, the small differences in local time became more than a curiosity. They became a problem. A train departing from Manchester at noon might arrive in Leeds at 12:52, not because it had taken 52 minutes, but because the two towns set their clocks differently. Schedules became confusing. Missed connections were common, and railway companies faced growing frustration from passengers who could not make sense of their timetables. The sun, once the undisputed master of time. In 1840, the Great Western Railway, under the direction of engineer Isambard Kingdom Brunel, made a bold decision. It would adopt a single standard time for all its operations. Based on the clock at the Royal Observatory in Greenwich, within a few years, other railway companies followed suit, creating what became known as railway time. Trains now ran on a unified schedule, and stations displayed Greenwich Mean Time rather than their own local solar time. The change brought immediate benefits to the railways, but it also created confusion and resistance in towns that had long defined their days by the sun. Church clocks continued to strike noon according to the heavens. Shopkeepers opened and closed on their own rhythms, and travelers often carried pocket watches set to both local and railway time to avoid missing their trains. The debate over standardized time grew heated. Critics argued that railway companies were imposing an artificial order on nature, severing the deep connection between daily life and the natural world. Newspapers published letters from farmers and clergy decrying the arrogance of letting machines dictate the hours. In Bristol, a city particularly resistant to the change, The public clock continued to show local solar time for years after the trains had switched, its face carrying 2-minute hands, one for Bristol time and one for Greenwich time, as if the city itself were caught between two worlds. Yet the demands of commerce, travel, and industry proved too strong to resist. By the 1850s, most British towns had quietly aligned their clocks with the railways, and in 1880, Parliament passed the Statutes Definition of Time Act, officially adopting Greenwich Mean Time as the legal standard across the United Kingdom. The ripple effects of this transformation reached far beyond Britain's shores. As railroads spread across Europe, North America, and the colonies, the problem of local time zones multiplied on a continental scale. In the United States, for example, noon in Boston was nearly 3 hours earlier than noon in San Francisco. Train companies faced chaos trying to coordinate transcontinental schedules. In 1883, American railroads took matters into their own hands, dividing the country into 4 standardized time zones and synchronizing their operations across thousands of miles. A year later, in 1884, representatives from 26 nations met in Washington, D.C. at the International Meridian Conference, where they adopted the Greenwich Meridian as the world's prime meridian and laid the foundation for a global timekeeping system. By the end of the century, the sun no longer ruled the hours, the clock did. This shift marked a profound change in humanity's relationship with time. For millennia, time had been a natural rhythm, rising and falling with the sun, the moon, and the seasons. Now it was a construct shaped by technology, commerce, and industry. Factories depended on synchronized shifts. Telegraph messages needed precise timestamps, and financial markets opened and closed according to the same minute across oceans. The day was no longer measured by the shadow's length on a church wall, but by the click of a telegraph relay or the schedule of an express train pulling into a distant station. Even language changed, as people began to speak not just of morning or evening, but of railway minutes and Greenwich time, symbols of a new era where precision and coordination mattered more than the movement of the heavens. Yet this new order was not simply about convenience. It was about control. The power to set time became the power to shape society. Governments could regulate work hours, coordinate military campaigns, and impose order on sprawling empires through the synchronized ticking of clocks. Railways, once a disruptive force, became instruments of authority, binding distant provinces and cities together under a single temporal framework. Time, once scattered across 1,000 church towers and village sundials, was now centralized, standardized, and industrialized, a resource to be managed, a tool to be wielded. By the close of the 19th century, the world had entered a new temporal landscape. People woke, worked, traveled, and slept according to schedules set not by the sun's passage across the sky, but by printed timetables, factory whistles, and government decrees. The transformation had begun with the humble steam engine and a need to keep trains from colliding. But its consequences reached into every corner of life. The clock had bent the hours to serve the machine, and in doing so, it reshaped humanity's understanding of time itself. From a natural flow that carried us forward to a system of human invention that told us precisely where we should be, and exactly when. At the dawn of the 20th century, the universe seemed as steady and predictable as the ticking of a clock. For more than 2 centuries, Isaac Newton's laws had offered a comforting picture of reality. Space was an unchanging stage. Time flowed at a constant rate for all observers, and events unfolded in a perfectly ordered sequence no matter where or how they were viewed. A second on Earth was a second on Mars, and a second in a moving train was the same as a second on a still platform. This view matched common sense and aligned neatly with the mechanical age that had followed the Industrial Revolution. Yet in 1905, a 26-year-old patent clerk in Bern, Switzerland, would dismantle that certainty with a few pages of handwritten equations and a simple but astonishing idea. Time is not absolute. Albert Einstein's paper on the electrodynamics of moving bodies, published in June 1905, introduced what he called the special theory of relativity. At its core was a radical proposition that the speed of light in a vacuum is the same for all observers, regardless of their motion, and that to preserve this constancy, both space and time must bend and stretch. The implications were shocking. Time, which had always been treated as a universal, unchanging background to events, was now revealed to be flexible, relative, dependent on the motion of the observer. A clock on a fast-moving train would run more slowly than a clock at rest. A twin traveling at near-light speed and returning home would be younger than his sibling who stayed behind. Seconds could lengthen or shorten not because of faulty machinery, but because of the fabric of the universe itself. Einstein's ideas were not widely accepted at first. They clashed with centuries of scientific tradition and challenged deeply held intuitions about reality. Yet over the next decade, he expanded his theory even further. In 1915, he published the General Theory of Relativity, which added gravity to the picture and showed that massive objects like stars and planets warp not just space but time itself. A clock placed near a massive body runs more slowly than one farther away. Time does not simply flow like a universal river. It bends, stretches, and twists around the contours of space and matter. Even something as familiar as standing on Earth's surface meant that our sense of time was being subtly distorted by the planets. Gravity, a fact that no one in Newton's era could have imagined. The first experimental hints that Einstein was right came from astronomy. In 1919, during a total solar eclipse observed from Sobral in Brazil and the island of Principe off the coast of Africa, Arthur Eddington and his team confirmed that starlight bent around the sun exactly as general relativity predicted. But even more direct evidence of time's slipperiness emerged in the decades that followed. As technology advanced enough to test Einstein's ideas here on Earth, one of the most striking demonstrations came in 1971, when physicists J.C. Haffel and Richard Keating flew for atomic clocks aboard commercial airliners around the world, twice eastward and twice westward, and compared them to identical clocks left at the U.S. Naval Observatory in Washington, D.C. The results were precise and undeniable. The airborne clocks showed measurable differences from the stationary ones, gaining or losing time depending on the direction and speed of their flights. Time had flowed differently simply because the clocks were moving. The experiments did not stop there. Throughout the 20th century, ever more sensitive tests confirmed that time dilation, the stretching or compressing of time predicted by relativity, was real. Muons, subatomic particles created by cosmic rays hitting Earth's atmosphere, live longer when moving at near-light speeds than they do at rest, precisely as relativity demands. In the 1950s and 1960s, scientists used synchronized atomic clocks to measure gravitational time dilation at different altitudes, demonstrating that clocks on mountaintops tick slightly faster than those at sea level. These effects, though minuscule in everyday life, become significant over large distances and high speeds, and today, they are woven into the infrastructure of modern civilization. One of the most familiar examples lies in the constellation of satellites orbiting above our heads. The Global Positioning System, which guides everything from smartphones to ships, depends on ultra-precise timing signals sent from satellites to receivers on Earth. But those satellites, moving rapidly and orbiting farther from Earth's gravity, experience time differently from clocks on the ground. Their onboard clocks tick about 38 microseconds faster per day than they would on Earth, a discrepancy tiny enough to seem irrelevant. Yet, if uncorrected, it would cause GPS errors to accumulate at a rate of about 10 kilometers per day. Engineers must account for both special and general relativity in their calculations. Proving that Einstein's once controversial theories are now essential to navigating the modern world. The deeper truth behind all these experiments is unsettling, but inescapable. There is no single, universal time shared by all observers. Time flows differently depending on where you are and how you move. And even the passage of a second, something we once believed to be constant, becomes a matter of perspective. A second on the summit of Mount Everest is not quite the same as a second at the bottom of the Mariana Trench. A second aboard the International Space Station is not identical to a second in your living room. Time, it turns out, is woven into the fabric of reality itself. And that fabric stretches and bends in response to motion and mass. For most of history, humans believed that time was a fixed backdrop, a cosmic metronome ticking evenly across the universe. Einstein shattered that illusion, revealing that the flow of time is not a universal beat but a complex, shifting rhythm different for every observer. In doing so, he changed not only physics, but our understanding of existence itself. Time is no longer a river carrying us forward in unison. It is a landscape warped and contoured, and we are travelers moving through it along paths that are never quite the same. The idea sounds like something out of science fiction, two identical twins born at the same moment. Living the same number of years, yet one returns from a journey through the cosmos younger than the other. It seems to break every rule of common sense. Because for most of human history, we believed that time was the one thing that treated everyone equally. Whether you were a farmer in ancient Mesopotamia or a sailor in the age of exploration. A second was a second, an hour was an hour, and everyone aged at the same pace beneath the turning of the heavens. But in the strange world described by Albert Einstein's theory of relativity, that comforting assumption crumbles. Time does not pass at the same rate for everyone. It can slow down or speed up, depending on how fast you move or how close you are to a source of gravity. And the deeper scientists have looked, the clearer it has become that time is not universal at all. It is personal. The so-called twin paradox is the simplest way to illustrate this unsettling truth. Imagine two identical brothers born seconds apart. One remains on Earth, living an ordinary life. The other boards a spacecraft capable of traveling at a significant fraction of the speed of light. He accelerates into space, travels for what seems to him a few years, then turns around and returns. To his surprise and ours, he discovers that while perhaps 5 years have passed on his journey, decades may have passed on Earth. His brother, now gray-haired and aged, has lived far longer. The traveling twin, however, has aged more slowly. The paradox is not a trick or a flaw in logic. It is a consequence of the way motion distorts the flow of time. The faster you move, the slower time passes for you, relative to someone who remains at rest. For much of the 20th century, this remained a thought experiment, a strange consequence of equations that few believed would ever be seen in reality. Yet with the rise of precise clocks and powerful aircraft, scientists began testing the effect and found that nature agreed with Einstein. One of the most famous real-world confirmations came in 1971, when physicists Joseph Haffel and Richard Keating carried out an experiment that brought the twin paradox down from the realm of theory to the surface of the Earth. They placed 4 highly accurate cesium atomic clocks aboard commercial airliners and flew them twice around the globe, once eastward and once westward. Upon their return, the airborne clocks were compared with identical ones that had remained stationary at the U.S. Naval Observatory in Washington, D.C. The results matched Einstein's predictions. The clocks on the eastbound flights had lost time, and those on the westbound flights had gained time relative to the ground-based clocks. The differences were tiny, only a few hundred billionths of a second, but they were real and measurable. Even at the modest speeds of passenger jets, time itself had shifted. Experiments like Haffel and Keating's are not just historical curiosities. They are repeated and refined constantly, and their results shape the technologies we rely on every day. Global positioning satellites, for example, orbit Earth at about 14,000 kilometers per hour and experience weaker gravity than we do on the surface. As a result, their onboard clocks tick slightly faster than identical clocks on Earth. Engineers must account for this difference. About 38 microseconds per day, or GPS navigation would drift by kilometers each day. In effect, every GPS satellite is living its own version of the twin paradox, experiencing time at a slightly different rate than we do on the ground. The most vivid example, however, unfolds continuously just above our heads. Astronauts aboard the International Space Station travel around Earth at roughly 28,000 kilometers per hour, circling the planet once every 90 minutes. Because of their high speed and slightly weaker exposure to Earth's gravity, Time for them moves just a bit slower than it does for those of us on the ground. Over the course of a 6-month mission, the difference amounts to only a few milliseconds, but it is measurable. When they return home, they are quite literally younger than they would have been if they had remained on Earth. The difference is too small to notice without precise instruments. But it proves that time does not flow evenly everywhere. It depends on your journey. This strange, personal nature of time has profound implications. It means that there is no single, universal clock ticking away in the background of the universe. Each of us carries our own private flow of time, determined by our motion and our place in gravity's field. Two people standing side by side share almost the same experience of time, but not quite. One might be slightly higher above sea level, experiencing a fractionally faster passage of seconds. A person climbing a mountain or flying across the sky is experiencing time differently than someone sitting at home. Even the Earth itself is engaged in this subtle distortion, the core of the planet. Deep within its stronger gravitational field, experiences time more slowly than the surface we live on. The twin paradox, then, is not a puzzle to be solved, but a window into the deeper structure of reality. It reveals that time is not a universal current flowing at the same rate for everyone, but a flexible dimension shaped by speed and gravity. The brother who stays behind and the brother who travels may share the same birth date and the same memories, but their journeys through time diverge the moment their paths part. One accumulates seconds more quickly, the other more slowly, and when they reunite, they are no longer the same age. What began as a mathematical curiosity in Einstein's notebooks has become a daily fact of life for pilots, astronauts, engineers, and scientists, and a profound reminder that time, like space, is not a fixed backdrop, but a landscape we move through individually. Each heartbeat, each journey, each orbit traces its own path through that landscape, proving that time is no longer a shared stage. It is a deeply personal story, written differently for each of us. For as long as people have tried to measure time, they've also tried to understand what it truly is. And long before scientists built clocks or physicists measured the curvature of space-time, philosophers wrestled with a deeper, more unsettling question. Does time actually move at all? The ancient Greek thinker Heraclitus, writing in the 6th century BCE, famously declared that everything flows, suggesting that the essence of reality is constant change and that nothing remains the same from one moment to the next. His image of a river, into which one can never step twice, because new waters are always flowing, shaped Western thought for centuries. Yet even in antiquity, not everyone agreed. Parmenides, a contemporary of Heraclitus, argued that change itself was an illusion, and that reality was static and eternal. The world, he believed, did not become. It simply was. These early arguments revealed a tension that still haunts our understanding of time. If change is real, then time must be something that flows. But if reality is unchanging and eternal, perhaps time does not move at all. The idea that time's passage might be an illusion gained new force in the modern era, particularly after the revolutionary discoveries of relativity. In the early 20th century, when Albert Einstein showed that time was woven together with space into a single four-dimensional fabric called space-time, philosophers began to reconsider what it meant to say that time flows. If all points in space exist from the summit of Mount Everest to the depths of the Pacific Ocean, why should we think that all points in time do not? Perhaps the past, present, and future all exist simultaneously, just as all places exist simultaneously. And what we call the passage of time is simply our movement through that four-dimensional landscape. This view came to be known as the block universe, a model in which time is not a river flowing from past to future, but a vast, unchanging structure in which every event from the birth of the universe 13.8 billion years ago to the reading of these words and beyond has a fixed location. One of the most influential arguments for this view came from the British philosopher J.M.E. McTaggart in the early 20th century. In a 1908 paper titled The Unreality of Time, he argued that time as we ordinarily conceive it is contradictory and therefore cannot exist. McTaggart distinguished between two ways of ordering events: the A series, which describes events as past, present, or future, and the B series, which orders them as earlier or later than one another. The A series, he argued, was essential to our experience of time, but it was also incoherent, because every event is, at different moments, future, then present, then past. This constant shifting of properties, he concluded, made time unreal. The B series, by contrast, described a timeless order of events, where one event is simply earlier or later than another, but it did not involve any flow. Many philosophers disagreed with McTaggart's conclusions, but his argument forced them to confront a possibility that most found deeply unsettling: that time does not pass at all. The block universe view fits surprisingly well with what physics tells us about reality. In Einstein's relativity, there is no universal now shared by all observers. To events that are simultaneous for one person may not be simultaneous for another, moving at a different speed or sitting in a different gravitational field. Without a universal present, the distinction between past, present, and future begins to lose its meaning, and what remains is a timeless spacetime where all events simply are. In this picture, the assassination of Julius Caesar in 44 BCE, the signing of the Declaration of Independence in 1776, and the first human footsteps on Mars decades from now, all exist equally within the block. We perceive only one slice of this vast structure at a time. Just as a traveler on a train sees only the scenery passing by his window, but the landscape itself does not move. Yet if the block universe is correct, and time does not flow, a difficult question remains. Why does it feel so powerfully as though it does? Our lives are saturated with a sense of passage. We remember the past, but not the future. We watch children grow and seasons change. We speak of time rushing or dragging, of hours slipping away and days stretching on. This undeniable psychological experience seems at odds with a static universe. Some philosophers and scientists suggest that the sensation of time's flow may arise from the way our brains process information. Each moment we experience is a new configuration of memories, sensory inputs, and expectations. As these configurations change, we interpret the change as motion, not of objects in space, but of time itself. Others argue that entropy, the natural tendency of the universe to move from order to disorder, gives rise to the arrow of time, creating a direction from past to future, even if all events coexist. Perhaps the truth lies somewhere between perception and physics. We are creatures that live one moment at a time, constructing narratives of before and after, cause and effect. To make sense of a universe that may not care about those distinctions, to us, the river of time feels as real as the river of water flowing under a bridge. Yet if we could somehow step outside our own perspective, if we could see the universe as a whole, from beginning to end, we might realize that the river never flows at all. The past has not vanished, the future has not yet appeared, and the present is not moving. Everything simply exists, timeless and complete. What we call the passage of time may be nothing more than the narrowness of our perspective. A trick of consciousness navigating a cosmos that, in its deepest nature, never changes. And if that is true, then time is not a river carrying us forward. We are the ones moving. Tracing a path through a landscape that was always there, there is a strange and stubborn truth about the world we live in, one so familiar that most of us never question it, yet so fundamental that without it, our understanding of time itself would collapse. It is the reason we grow older and never younger. Why ice melts into water, but water never freezes itself into a perfect cube on a summer sidewalk. Why a dropped glass shatters into 1,000 glittering shards. But those shards never leap back into your hand and reassemble into their original form. This truth is the second law of thermodynamics, the principle that in any closed system, disorder, what scientists call entropy, always increases. It is not a law about clocks or calendars, and it does not care about minutes or hours. But it quietly dictates the direction of time itself. Without entropy, time might not seem to flow at all, and the difference between past and future would lose its meaning. The story begins in the early 19th century, When scientists like Sadi Carnot, Rudolf Clausius, and Lord Kelvin were grappling with the puzzling behavior of heat and energy, they observed that when energy changes form, as when steam drives a piston or a fire warms a room, it tends to spread out. It's becoming less concentrated and less useful for doing work. Clausius, writing in the 1850s, introduced the term entropy to describe this tendency toward disorder, and he formulated the second law to express a universal truth. The total entropy of an isolated system can never decrease over time. It can stay the same in idealized, reversible processes, but in reality, it always increases. In simple terms, this means that energy naturally disperses. Structures break down, and order gives way to chaos. This increase in entropy is not just a fact about steam engines or laboratory experiments. It is a principle woven into the fabric of the universe. Every time you strike a match, the concentrated chemical energy in the wood disperses as heat and light. Every time you breathe, the orderly molecules of oxygen and carbon dioxide mix and spread through the air. Even the stars in the night sky, burning hydrogen into helium in their blazing cores, are slowly diffusing their energy into space, pushing the cosmos toward a colder, more uniform state. The second law is why we age, and why memories belong to the past and not the future. It is why a cup of coffee left on a table will always cool to room temperature and never spontaneously heat itself up again. These everyday examples are so familiar that they seem trivial. Yet they are all manifestations of the same fundamental truth. Entropy increases, and with it, time moves forward. This link between entropy and time's direction is often called the arrow of time, a phrase coined by the British astronomer Arthur Eddington in 1927. Unlike the laws of motion or gravity, which work the same way forward or backward, the second law gives the universe a preferred direction, from order to disorder, from the improbable to the inevitable. You can film 2 billiard balls colliding and play the footage in reverse, and it will look plausible because the underlying physics is symmetrical. But film a shattered glass rising from the floor and reforming in midair, and the illusion breaks instantly because it violates the second law. The arrow of time points from the low entropy past to the high entropy future, and it does so with relentless certainty. Yet this raises a deeper, more puzzling question. If entropy always increases, why was it ever low to begin with? Why did the universe start in such an improbable, highly ordered state? Cosmologists have wrestled with this mystery for decades, and while no one has a definitive answer, the most widely accepted explanation traces it back to the birth of the universe itself. When the Big Bang occurred 13.8 billion years ago, the universe was unimaginably hot and dense. But it was also remarkably smooth and uniform conditions that correspond to low entropy on a cosmic scale. As the universe expanded and cooled, gravity began to clump matter into stars and galaxies, creating pockets of order within a growing background of disorder. It is this initial low-entropy state, this improbable cosmic starting point, that gives the arrow of time its direction today. In a sense, the flow of time is not a fundamental feature of nature, but a consequence of the universe's strange and unlikely birth. The connection between entropy and time also helps explain why we remember the past but not the future. Memory, after all, is a process of recording order, a pattern of neural activity shaped by past events. Once those events have occurred, they are part of the low-entropy past. The future, by contrast, is high entropy and undetermined, filled with countless possible outcomes that have yet to take shape. Our minds, like our coffee cups and our galaxies, are bound to the arrow of time, moving from the ordered to the disordered, from the known to the unknown. Even consciousness itself may be a reflection of this one-way journey, a pattern of perception built atop the irreversible march of entropy. And yet, for all its power, the second law is not a tyrant, but a tendency. On small scales, and over short periods, fluctuations can temporarily decrease entropy. A patch of air might spontaneously cool slightly, or a few molecules might clump together against the odds, but these are statistical exceptions. fleeting ripples in a vast tide. On the scale of stars, planets, and living beings, the direction is unchanging. Disorder grows, structures collapse, energy spreads, and time moves ever forward. It is tempting to think of time as something flowing independently of the physical world, a cosmic clock ticking somewhere beyond our reach. But the arrow of time is not a separate force. It is the sum of countless irreversible processes happening all around us. From the decay of radioactive atoms to the slow fading of galaxies. It is the reason a broken egg cannot unbreak, and why the ashes of a fire never leap back into a log. In the end, what we call time's passage may be nothing more than entropy's steady advance. The universe's drift from order to disorder, and the faint memory of a beginning that set it all in motion. It is, in that sense, a cosmic accident, a byproduct of an improbable birth, and a reminder that even the deepest mysteries of existence may arise not from inevitability, but from chance. If you look up into the night sky and let your eyes wander beyond the familiar patterns of stars, beyond the drifting glow of the planets and the hazy arch of the Milky Way, you are gazing into a universe that keeps time with a precision no human clock can match. Long before people carved sundials into stone or built atomic clocks in laboratories, the cosmos was already ticking away with rhythms, so regular and predictable that they have become essential to how we measure and understand the passage of time itself. These rhythms are not measured in seconds or hours, but in pulses, rotations, orbits, and echoes that stretch across billions of years. They are the beating hearts of stars, the lingering whispers of the Big Bang, and the silent dance of worlds around their suns. And yet beneath their precision lies a deeper question. Are these cosmic patterns the essence of time? Or are they merely the motions through which time reveals itself? One of the most astonishing examples of nature's timekeepers is the pulsar, a type of neutron star born in the aftermath of a supernova. The catastrophic death of a massive star. When such a star collapses under its own gravity, its core is crushed into a sphere barely 20 kilometers across. Yet containing more mass than our entire sun, these remnants spin at staggering speeds, some hundreds of times per second, and emit beams of electromagnetic radiation from their magnetic poles. As they rotate, these beams sweep across space like the beam of a lighthouse, and when one happens to point toward Earth, we detect it as a pulse of radio waves, perfectly timed and astonishingly regular. The first pulsar, discovered in 1967 by Jocelyn Bell Bernal and Anthony Hewish, pulsed every 1.337 seconds with such precision that the team briefly wondered if it was an alien signal. Today we know that some millisecond pulsars are so consistent they rival the best atomic clocks on Earth. Their rotational periods, varying by less than a millionth of a second over decades. This cosmic regularity is not just a curiosity, it is a tool. Astronomers use pulsars as celestial metronomes to probe the fabric of space, test Einstein's theories, and even navigate spacecraft. The Pioneer 10 and 11 probes, launched in the early 1970s and now drifting toward interstellar space, carry metal plaques depicting the positions and pulse frequencies of 14 known pulsars. Any intelligent civilization that finds them millions of years from now could use those pulsars as a galactic map and clock. Tracing the probe's origin back to Earth and the era when they were launched, decades later, NASA's NICER experiment aboard the International Space Station demonstrated that pulsars could be used as natural navigation beacons, guiding spacecraft through deep space without relying on Earth-based signals. Even more ancient and omnipresent than pulsars is the faint microwave glow that fills the universe in every direction, the cosmic microwave background, or CMB. This radiation is the afterglow of the Big Bang itself, released when the universe cooled enough for atoms to form about 380,000 years after its violent birth, roughly 13.8 billion years ago. The CMB is not a clock in the usual sense, but it is a cosmic time stamp, a frozen record of a moment when the universe transitioned from opaque plasma to transparent space. By measuring tiny fluctuations in the CMB's temperature and distribution, scientists can trace the expansion history of the cosmos and determine its age with remarkable precision. The fact that we can assign a number, 13.799 plus or minus 0.021 billion years, to the universe's age is itself a testament to the clock-like reliability of cosmic processes. Unfolding on unimaginable scales, planetary motion offers another example of the universe's natural timekeeping. Since Johannes Kepler published his laws of planetary motion in the early 1600s, astronomers have understood that the orbits of planets follow precise mathematical patterns governed by gravity. The Earth's journey around the Sun defines the year. The Moon's orbit defines the month, and the planet's rotation defines the day. These motions are so consistent that they have guided calendars, agricultural cycles, and religious rituals for thousands of years. On a larger scale, orbital mechanics enable us to navigate the solar system itself. When NASA's Voyager 1 spacecraft launched in 1977, engineers used precise calculations of planetary alignments and gravitational assists to slingshot it past Jupiter and Saturn, sending it on a trajectory that would eventually carry it beyond the heliosphere. That mission depended not just on accurate clocks on Earth, but on the predictable ticking of celestial mechanics, the dance of planets. It repeats with unwavering regularity over millennia. But as we rely on these cosmic rhythms to mark and measure time, an unsettling question lingers beneath the surface. Are pulsars, orbits, and radiation truly manifestations of time, or are they merely motions unfolding within it? A pulsar spins, but does its steady pulse create time, or simply divide it into measurable intervals? The Earth circles the Sun every 365 days, but would time still pass if the planet suddenly stopped moving? Even the cosmic microwave background, a snapshot frozen billions of years ago, is a record of change. But does change itself define time, or does it occur within a deeper, unseen framework? Philosophers and physicists continue to wrestle with this question, and the answer remains elusive. Perhaps time is nothing more than the sum of these motions. It's a convenient abstraction that emerges from the ceaseless unfolding of the universe. Or perhaps motion is merely our way of perceiving something far more fundamental, a hidden dimension woven into the fabric of reality that continues whether anything moves or not. What we know for certain is that these cosmic rhythms, from the heartbeat of a pulsar to the stately orbit of a planet, are the closest we have to eternity's clock. They keep their steady beat across billions of miles and billions of years, indifferent to the rise and fall of civilizations and the fleeting moments of human history. And so, when we look to the sky for the measure of our days and the age of our universe, we are not just reading a cosmic calendar, we are glimpsing the order and structure that underlies reality itself. Whether these rhythms are time or merely its footprints is a mystery we may never solve. But they remind us that the universe has been keeping its own quiet count long before we learn to mark the passing of seconds. And it will continue long after our last clocks have stopped. If time feels abstract when we speak of clocks and calendars, it becomes something entirely different when we walk along a windswept cliff or trace. Our fingers over the ridges of a fossil embedded in stone. Nowhere is the scale of time more humbling, more vast, and more incomprehensible than in the layers of the earth itself. Every rock, every sediment deposit, every ripple frozen in sandstone is a page in a story that began long before the first human breath and will continue long after the last. It is a story written not in words but in minerals, pressures, and temperatures, in the slow drift of continents and the rise and fall of oceans, in the relentless work of wind and water carving valleys and mountains over spans so long they defy ordinary language. And it was not until a handful of thinkers and explorers in the late 18th and 19th centuries began to read those pages that humanity truly understood how small its own history was against the immensity of geological time. The Scottish geologist James Hutton is often called the father of this revelation. In the 1780s, he spent long days traversing the rugged coastlines and riverbanks of his homeland, hammer in hand, notebook tucked under his arm, searching for clues to the Earth's history. At a site now famous as Syccar Point on the coast of Berwickshire, he found an extraordinary outcrop, layers of nearly vertical grey-wax sandstone. Formed on the ocean floor millions of years earlier, overlaid by horizontal beds of red sandstone. The contact between them, an unconformity, as geologists later called it, revealed a sequence of unimaginable events. The older rocks had been laid down in ancient seas, compressed into stone, thrust upward, tilted, and eroded before new layers were deposited on top. The implications staggered Hutton. This was not the work of a few thousand years, as biblical chronology then suggested, but of hundreds of millions. "We find no vestige of a beginning," he wrote in 1788. "No prospect of an end." With that sentence, the human understanding of time expanded beyond all previous bounds. Hutton's ideas were radical, and not everyone accepted them. Many still clung to a world only a few thousand years old, shaped by a single catastrophic flood. But fieldwork kept uncovering evidence that the Earth was older, far older than anyone had dared imagine. Charles Lyell, writing in the 1830s in his monumental Principles of Geology, built on Hutton's insights and argued for a vision of Earth shaped by slow, continuous processes over vast stretches of time. Rivers carved valleys grain by grain, coral reefs grew centimeter by centimeter, mountains rose imperceptibly through countless generations. Lyell called this principle uniformitarianism, the idea that the present is the key to the past. By studying the forces shaping the world today, geologists could infer the forces that shaped it millions or even billions of years ago. Field expeditions in the 19th and 20th centuries further deepened this understanding. Explorers and scientists traveled to the Grand Canyon in the American Southwest, where layer upon layer of ancient rock stretches more than a mile deep, exposing nearly 2 billion years of Earth's history. They mapped the towering limestone cliffs of the Dolomites in Italy, once ancient seabeds teeming with life. They drilled into the Greenland ice sheet, retrieving cores that recorded hundreds of thousands of years of climate change in thin layers of compressed snow. And in Africa's Great Rift Valley, they uncovered volcanic ash layers that bracketed the fossils of early humans. Anchoring our own species' story within the immense sweep of geological time, the discovery of radioactivity in the late 19th century added a powerful new tool to the study of deep time. In 1905, physicist Ernest Rutherford proposed that the decay of radioactive elements within rocks could serve as a natural clock, measuring the time since the rock formed. Using this method, scientists gradually pieced together a timeline of Earth's history. The numbers they found dwarfed anything previously imagined. The planet, they concluded, was not 6,000 years old, nor even a few million, but roughly 4.54 billion years, a span so vast that the entire history of human civilization, from the first cities in Mesopotamia to the present, occupies less than a blink of an eye in comparison. Understanding this immensity has transformed not only geology, but every science that touches on the past. Evolution, once criticized as too slow to explain the diversity of life, became not just plausible, but inevitable when stretched over hundreds of millions of years. The slow drift of continents, described by Alfred Wegener in 1912 and confirmed decades later as plate tectonics, explained the rise of mountain ranges and the distribution of fossils across continents now separated by oceans. Even climate change, often discussed in terms of decades or centuries, takes on a deeper meaning when viewed against the backdrop of ice ages and greenhouse. It's epochs that have cycled across the planet for hundreds of millions of years. But perhaps the most profound impact of the concept of deep time is philosophical. It forces us to confront the brevity of our existence, to realize that human history, the rise and fall of empires, the writing of books and building of cities is a fleeting chapter in a story. It began long before us and will continue long after we are gone. The granite peaks of the Himalayas, which seem eternal to us, are young in geological terms. Still rising from the collision of continents that began only 50 million years ago, the oldest known zircon crystals, discovered in Western Australia and dated to 4.4 billion years, formed when the Earth itself was barely cool enough to sustain a crust. Against such measures, the human lifespan is almost nothing, a spark in a night that began before time as we know it. And yet, in that vastness, there is a strange kind of comfort. The rocks beneath our feet are not just inert matter. They are the memory of the planet, recording every chapter of its long story. To read them is to stretch the mind beyond its usual boundaries, to grasp, however imperfectly, the scale of time that shaped our world. It is to understand that the ground we stand on was once seabed, that the mountains we climb were once plains, that the air we breathe has been breathed by creatures long vanished. In this way, geology does more than measure time. It deepens our sense of belonging within it, reminding us that we are part of a continuum far older and larger than ourselves, and that our brief moment, though fleeting, is written into the same story as the ancient stones, long before the first clock tower rose above a medieval town square, long before atomic oscillations defined the length of a second. Living things were already keeping time, not with gears or pendulums, but with patterns written into their bodies and behavior. Time is not only measured by the swing of a pendulum or the orbit of a planet. It is also etched into the beating of a heart, the rise and fall of hormones, the division of cells, and the slow unfolding of a life from birth to death. From the smallest bacterium to the tallest tree, from the migrations of monarch butterflies to the sleep cycles of humans, biology itself is a vast network of clocks, each ticking to rhythms older than humanity, older even than the continents themselves. We often think of time as something outside of us, a force that acts upon our lives. But the truth is that time is woven into our very flesh, and it moves us as surely as the Earth's orbit around the sun. One of the most fundamental biological clocks is the circadian rhythm, a roughly 24-hour cycle that governs countless processes in almost every living thing. The word circadian comes from the Latin circa diem, meaning about a day, and it is no coincidence that this rhythm mirrors the planet's rotation. In humans, it regulates when we sleep and wake, when our body temperature rises and falls, when hormones like cortisol and melatonin are released, and even how our metabolism changes throughout the day. This rhythm is not dictated by alarm clocks or work schedules. It is generated internally by a cluster of about 20,000 neurons in a region of the brain called the suprachiasmatic nucleus, located in the hypothalamus. This tiny structure acts as the body's master clock, synchronizing our internal cycles with the external world by responding to cues like light and darkness. When sunlight hits the retina in the morning, it signals the clock to reset, aligning the body's rhythms with the day. When night falls, melatonin levels rise, preparing us for sleep. Every day, this internal metronome ticks on, guiding the countless processes that keep us alive. Yet circadian rhythms are only one layer of biology's complex relationship with time. On larger scales, animals follow seasonal rhythms that span months or even years. Migratory birds like the Arctic tern travel tens of thousands of kilometers between hemispheres with astonishing precision, timing their departures to seasonal shifts in daylight and temperature. Salmon return from the open ocean to the rivers of their birth after several years at sea, their journeys guided by internal calendars that track not only time but also environmental cues. Even plants keep time. Many species flower or shed leaves in response to the length of daylight, a phenomenon known as photoperiodism. These cycles are not conscious decisions, but biological imperatives, encoded in DNA and honed by millions of years of evolution to ensure survival in a changing world. On a deeper level still, time shapes life itself. Every cell in the human body contains molecular clocks that regulate when genes are expressed, and cells divide and when they die. The shortening of telomeres, the protective caps at the ends of chromosomes, acts as a biological timer that limits how many times a cell can divide, a process linked to aging and the eventual decline of tissues and organs. The rhythms of growth and decay play out over decades. Bones fuse in adolescence. Reproductive cycles change with age, and the heart, which beats about 100,000 times a day, will have pulsed more than 2.5 billion times in a typical human lifetime. Even the brain, which seems timeless in its thoughts, follows these biological cadences, slowing its processing speed with age and altering its patterns of sleep and memory. If biological time is so deeply embedded in us, what happens when it is removed? That question has fascinated scientists for decades, and some of the most revealing experiments have taken place in the strangest of settings, deep underground, far from any cues of day or night. In the 1960s, French speleologist Michel Siffer conducted a pioneering experiment by isolating himself in a cave beneath the French Alps for 2 months, with no natural light, no clocks, and no external signals of time. Deprived of the sun's daily rhythm, Siffer's internal clock began to drift. His sleep-wake cycles stretched beyond 24 hours, sometimes to 36 or even 48, and he lost all sense of how much time had passed. At one point, he believed that only a few weeks had gone by, when in fact 2 months had passed. Similar experiments, repeated by scientists in the decades since, have shown that humans possess an internal rhythm that can persist without external cues. But it is not perfectly aligned with the 24-hour day. Without the sun to reset it, our biological clocks gradually slip, revealing just how much our sense of time depends on our environment. These experiments expose a deeper truth. Our perception of time is not merely a response to the world outside. It is constructed from within. Our bodies are full of oscillations and cycles, from the flicker of neuronal activity in the brain to the monthly rhythms of fertility. And these cycles anchor us in a temporal framework even when the world offers no guidance. When that framework is disrupted by isolation, jet lag, or even the relentless artificial lighting of modern cities, our health suffers. Sleep disorders, metabolic problems, and mood disturbances all arise when our internal clocks are out of sync with the external day. The modern world, with its 24-hour work schedules and glowing screens, constantly challenges the ancient rhythms our bodies evolved to follow. And yet, despite our technologies and our attempts to master time, we remain creatures bound by it. We cannot stop the shortening of telomeres or the slowing of our hearts, nor can we escape the cyclical patterns that govern our behavior. Even the most advanced medicine can only slow the biological clock, not halt it. In this sense, time is not an external force pressing down on us. It is us. It is in the genes that switch on and off with the dawn, in the migrations that carry species across oceans, in the pulses of hormones that guide our moods, and in the inexorable progression of aging that shapes our lives from beginning to end. We are, in a profound sense, living clocks, and our very existence is a testament to the passage of time. Our hearts keep its beat, our cells count its steps, and our bodies, from the first breath to the last, are instruments built to measure the movement of the universe, whether we are aware of it or not. For as long as humans have been aware of their own mortality, they have searched for ways to outrun it, to stretch the narrow window of life a little longer, or even to step outside the relentless flow of time altogether. The ticking of a clock can be ignored, but the ticking inside the body, the gradual weakening of muscles, the graying of hair, the steady shortening of telomeres cannot. Time, in its most intimate and merciless form, is written into biology, and every heartbeat is a reminder that it cannot be stopped. Yet throughout history, and especially in the modern scientific age, people have tried to challenge that certainty, experimenting with ways to slow, suspend, or even reverse the passage of time as it applies to living things. Some of these efforts border on science fiction. Others are grounded in hard biology and physics. But all are driven by the same primal fear, the fear of running out of time. One of the most striking approaches to defying time's effects on life is cryonics, the practice of cooling organisms to extremely low temperatures in the hope of preserving them for future revival. The idea took shape in the mid-20th century, inspired partly by discoveries in nature and partly by advances in refrigeration and biology. In 1967, an American psychologist named James Bedford became the first person to undergo cryonic preservation. His body cooled and stored in liquid nitrogen after death, with the hope that future science might one day revive him. More than half a century later, Bedford remains preserved at 196 degrees Celsius. His cells frozen in a state where chemical reactions have essentially stopped. Today, organizations like Alcor Life Extension Foundation in Arizona and the Cryonics Institute in Michigan offers similar preservation services, storing hundreds of clients who hope that medical technologies of the future will repair the damage caused by aging, disease, and freezing itself. Critics argue that revival may never be possible. Ice crystals can rupture cells, and complex neural structures might not survive intact, but the principle behind cryonics taps into something deeply compelling. If time's damage comes from chemical change, then perhaps stopping those reactions is the same as stopping time. Nature, however, has been performing its own experiments in suspended animation for millions of years, and it has produced creatures whose survival strategies seem to defy the ordinary rules of biology. Among the most remarkable are tardigrades, microscopic eight-legged animals discovered in 1773 by German zoologist Johann Goes, and often called water. Bears tardigrades can enter a state called cryptobiosis. When conditions become extreme, such as intense cold, dehydration, or a lack of oxygen. In this state, they lose nearly all their water. Their metabolism slows to 0.01% of normal, and their biological activity effectively pauses. They have been revived after more than 30 years of dormancy and have even survived exposure to the vacuum of space. Other organisms display similar abilities. Wood frogs can freeze solid during winter. Their hearts and breathing stopped completely, only to thaw and resume life in the spring. Seeds of ancient plants have germinated after being trapped in permafrost for thousands of years. In each case, life does not escape time, but it does something extraordinary. It waits it out. Inspired by such examples, scientists have sought ways to induce suspended animation in larger organisms, including humans, with varying degrees of success. In 2005, researchers at the Fred Hutchinson Cancer Research Center in Seattle reported that they could place mice into a reversible hibernation-like state by exposing them to small amounts of hydrogen sulfide gas, which temporarily suppressed their metabolism and body temperature. The mice appeared dead, their breathing stopped. Their body temperature dropped to near ambient levels, but after a few hours, they were revived without harm. Such research hints at future medical applications, particularly in trauma care and space exploration. If doctors could slow a patient's metabolism after severe injury, they might buy precious hours for treatment. If astronauts could enter suspended animation during long-duration missions, they might survive journeys that would otherwise be impossible. Yet the science of slowing or stopping time at the biological level remains fraught with challenges. Cooling tissues too quickly can cause ice crystals to form, destroying cells. Metabolic suppression in complex organisms can trigger irreversible damage if not precisely controlled. Even in cryonics, where preservation has been achieved, revival remains speculative, reliant on technologies that do not yet exist. Despite these obstacles, research continues, driven by both scientific curiosity and human longing. Projects funded by NASA and the European Space Agency explore hibernation technologies for future Mars missions. Medical teams experiment with therapeutic hypothermia to preserve brain function after cardiac arrest. Each attempt is a step toward the dream of suspending life without ending it, of pausing the biological clock. Beneath all these efforts lies a profound intersection of biology, physics, and philosophy. To stop time biologically is to interfere with processes that have been constant for billions of years: metabolism, cellular respiration, chemical reaction. It is to step into a domain where physical laws and biological systems meet. In a sense, the search for suspended animation is a search to manipulate entropy itself, to halt the disorder that accumulates in living cells over time. And behind this scientific ambition lies an emotional truth that is as old as humanity. We are terrified of endings. The frozen body in a cryonics facility, the seed locked in Siberian permafrost, the tardigrade drifting in suspended animation. Each is a symbol of our refusal to accept that time always wins. It is unlikely that we will ever truly stop time, at least not in the way science fiction imagines. But perhaps the deeper point is not to freeze time forever, but to bend it. To slow its relentless pace just enough for life to catch its breath. Whether through cryopreservation, metabolic suppression, or the extraordinary resilience of nature's most durable organisms. The pursuit of suspended animation is more than a scientific endeavor. It is a reflection of humanity's deepest desire to endure. And even if the clock cannot be stopped, every attempt to press pause reveals something profound about our relationship with time, that we are not merely its victims, but its students, learning to stretch and shape it, even as it carries us forward, high in the thin air of the Andes, where the wind never warms and the snow does not melt even under a fierce summer sun. There are places where time seems to stop. On these peaks, above 6,000 meters, where even the hardiest vegetation cannot grow, archaeologists have uncovered scenes that appear frozen not only in ice but in history itself, offerings, artifacts, and most hauntingly, human bodies that have lain untouched for centuries, their skin, hair, and clothing preserved as though they had fallen asleep only yesterday. These discoveries are more than remarkable accidents of nature. They are windows into a past that did not vanish, but instead paused, waiting patiently in the cold for someone to arrive centuries later and bear witness. And in their stillness, they pose questions about time and death that no clock can answer, whether an ending is a single instant or a gradual fading, and whether the past is ever truly gone. One of the most extraordinary of these discoveries came to light in 1999 on the summit of Lulalaco, a dormant volcano that straddles the border between Chile and Argentina. At 6,739 meters above sea level, it is one of the highest archaeological sites on Earth, and the expedition that reached its summit that year, led by archaeologist Johann Reinhard and his Argentine colleague Constanza Cerruti, uncovered something that stunned the scientific world. Buried beneath layers of rock and ice were 3 children, a boy and 2 girls, who had been sacrificed by the Inca more than 5 centuries earlier. They were not skeletons or desiccated mummies like those found in desert tombs. They were perfectly preserved, their faces serene, their braided hair intact, their ceremonial clothing vibrant in color. The cold, thin, oxygen-poor air had halted the usual processes of decay, leaving them suspended in a state that blurred the line between life and death. The youngest of the 3, a girl no more than 6 years old, was wrapped in a fine textile and seated cross-legged, as if in meditation. The oldest, known as La Donzella, or the Maiden, was about 15 and had been chosen, according to Inca custom, for her purity and beauty. Her expression, calm and almost peaceful, suggested that she had slipped into unconsciousness before death, likely induced by coca leaves and chicha, a fermented maize drink, given to dull fear and pain. These children were offerings to the gods, part of a ritual known as capuca performed by the Inca to ensure fertility, avert disasters, or honor important events. To those who carried out the sacrifice, the act was not one of cruelty, but of profound religious devotion. And yet, standing before these frozen figures centuries later, it is difficult not to feel the tension between that ancient worldview and our own. Between their conception of time as cyclical and sacred, and our instinct to see it as linear and irreversible. For archaeologists, discoveries like those at Lulalaco are not just evidence of ancient practices. They are moments where time itself seems to pause. In the dry deserts of Peru, a body may mummify over centuries, slowly surrendering moisture until only skin and bone remain. In the jungles of Mesoamerica, monuments are swallowed by vegetation, erased grain by grain. But here, in the cold silence of the Andes, there is no gradual erasure. The wind does not rot flesh. The bacteria that devour tissue cannot survive, and the relentless march of decay is slowed to a crawl. The result is not merely preservation, but suspension. A historical moment captured mid-breath. Objects buried alongside the children, from feathered headdresses to miniature gold statues, remain as they were placed, untouched by time. Even the contents of the children's stomachs, analyzed centuries later, reveal what they ate in the days and hours before their deaths. Such preservation challenges our usual understanding of time's passage. Archaeology often deals with layers, the slow accumulation of sediment, the buildup of civilizations atop their predecessors, the steady collapse and rebuilding of human societies. But frozen sites like Lulalaco offer no layers, No gradual transitions, only sudden stillness. They are interruptions in the story, moments when the past refuses to recede into the distance. This stillness forces us to confront questions that reach beyond science. If the body does not decay, has death truly completed its work? Is the end of life a single, irreversible instant, or does it unfold across centuries as cells, memories, and meanings slowly dissolve? The question becomes even more complex when we consider that the frozen past is not entirely dead. Modern forensic techniques can extract DNA from these preserved remains, revealing genetic lineages and ancestral connections. Chemical isotopes in their hair can trace the journeys they took across the empire before their final climb. Even the microscopic bacteria in their mouths provide clues about ancient diets and diseases. In this way, the frozen dead continue to speak, their bodies yielding information that bridges the gap between their time and ours. It is as though time, rather than erasing them, has simply folded around them, holding them in suspension until we were ready to listen. There is something deeply unsettling, profoundly human about our reaction to these discoveries. We cannot help but see ourselves reflected in these frozen children, caught between motion and stillness, life and death. They remind us that time is not always a steady flow. Sometimes it halts, eddies, or freezes entirely, leaving fragments of the past standing in the present like ghosts that refuse to leave. They remind us, too, that death is not a simple boundary, but a process, one that can be delayed, preserved, and revisited even centuries after the last heartbeat. Standing on that icy summit, with the wind howling and the world stretching endlessly below, it is impossible not to feel the weight of those centuries pressing close. The children of Lulalaco have been there since before Europeans set foot on the continent. Since before the Spanish conquest shattered the Inca world, since before the calendar we now use was even devised. Time, which swept away empires and languages and erased the names of those who once prayed for rain, has left them untouched. And in their perfect stillness lies a truth we often forget, that time is not only a destroyer, but a preserver, not only a river, but a glacier. It flows, but it also pauses, and in those pauses, the past waits patiently for the living to arrive. Humanity has always lived under the shadow of time. Yet one of the most revealing truths of history is that time itself, or at least its measurement, has never been neutral. From the earliest calendars carved into stone to the seconds displayed on our digital devices today, time has been shaped, redefined, and wielded as a tool of power. It is not simply a reflection of the sun's rising and setting or the passing of seasons, but often a deliberate construct imposed from above, a way for rulers to assert authority, to bind societies together under a shared rhythm, and to make obedience part of the daily structure of life. To change how people measure time is to change how they think, how they work, and even how they perceive their place in the world. Across centuries and continents, those in power have repeatedly sought to bend time to their will, and in doing so, they have shown just how deeply political the clock can be. The story begins in ancient Rome, where time was as much a tool of statecraft as of science. By the 1st century BCE, the Roman calendar had fallen hopelessly out of sync with the seasons. Based on a lunar system that failed to align with the solar year, it required constant manual adjustments by priests, adjustments that were often manipulated for political gain. By extending or shortening the year, magistrates could lengthen their terms or delay elections. In 46 BCE, Julius Caesar, newly declared dictator, decided to end the chaos. With the help of the Alexandrian astronomer Sosiagenes, he introduced a new solar-based system, the Julian calendar, which reorganized the year into 365 days with a leap day every 4 years. It was more accurate, more predictable, and, crucially, more centralized. The reform was not just a scientific improvement, it was a declaration that time itself now flowed according to imperial decree. Days and months no longer followed the unpredictable rhythms of the moon, but the measured, regulated order of Roman power. This intertwining of time and authority resurfaced centuries later in a far more radical form during the French Revolution. The revolutionaries who stormed the Bastille in 1789 sought not only to overthrow monarchy and privilege, but to erase the old order from every corner of society, including the calendar. In 1793, the National Convention introduced the French Republican calendar, a bold attempt to reshape how citizens experienced time. The year was divided into 12 months of 30 days each, with names like Thermidor and Fructidor, evoking nature rather than saints. Weeks were replaced with 10-day decades, intended to break the association with the Christian 7-day week and the Sabbath. Even the hours of the day were decimalized, with 10 hours of 100 minutes each. The calendar was a statement of ideology. Time itself would no longer reflect the rhythms of monarchy and church, but the rational order of reason and revolution. It was a tool of obedience as much as liberation, designed to wean citizens from centuries-old habits and to embed the revolution's principles into the very structure of their daily lives. But the experiment revealed the limits of political power over time. People resisted the new system, clinging to the familiar patterns of the old calendar. Farmers ignored the new month names, priests continued to mark Sundays, and factory workers struggled with the 10-day work cycle. After just 12 years, in 1805, Napoleon Bonaparte abolished the Republican calendar, restoring the Gregorian system that Pope Gregory XIII had introduced in 1582 to refine Caesar's original reforms. Yet even in failure, the episode demonstrated how deeply rulers understood the link between time and control. To change the calendar was to attempt to change consciousness itself. Elsewhere, other regimes followed similar paths. In 1929, Joseph Stalin's Soviet Union introduced a 5-day workweek, abolishing the traditional 7-day rhythm in an effort to maximize industrial output and weaken religious observance. Each worker was assigned one of 5 rest days, ensuring that factories never stopped. But the plan disrupted family life and community rituals, and it too was eventually abandoned. In 1975, North Korea instituted its own Jukki calendar, resetting the year count to 1912, the birth year of Kim Il-sung, effectively anchoring time itself to the life of the nation's founder. Even today, in places like North Korea or Saudi Arabia, official calendars carry ideological weight, structuring memory and history around religious or political milestones rather than astronomical cycles. Yet the manipulation of time has never been limited to authoritarian regimes. Even democratic societies have used it as a tool for coordination and control. The adoption of standardized time zones in the 19th century, driven by railway companies and later enforced by governments, imposed a new temporal order on populations who had once lived by local solar time. Colonial empires imposed European calendars on indigenous peoples, erasing older systems of reckoning seasons and festivals. International treaties fixed the prime meridian at Greenwich in 1884, giving Britain then the dominant naval and industrial power, not just geographic but temporal authority over the globe. In every case, the reorganization of time was more than a technical change. It was a political act, reinforcing hierarchies and shaping identities. The deeper question behind all these efforts is what happens when societies attempt to rewrite time itself. The answer is that they rarely succeed completely, but the attempt itself leaves deep marks. Calendars, once changed, alter how people remember the past and imagine the future. They redefine anniversaries, reshape rituals, and reorder priorities. When Julius Caesar fixed the length of the year, he made the empire's expansion easier to coordinate. When the French revolutionaries renamed the months, they tried to erase centuries of Christian dominance. When colonial powers imposed the Gregorian calendar on distant peoples, they also imposed their worldview. Time may seem like an impartial backdrop to history, but in reality, it is one of history's most contested arenas. Each reform, each calendar, each decree is an attempt to harness something universal and make it serve a particular vision of order. And in this struggle, a profound irony emerges. Even as rulers claim to control time, time ultimately controls them. Empires rise and fall, ideologies flourish and fade, but the days and seasons continue, indifferent to who names them. And yet, the urge to rewrite time persists not because humans can stop its flow, but because in shaping how it is measured, they shape how it is lived. In the deepest corners of physics laboratories, where sunlight never reaches and vibrations from footsteps above are carefully dampened by layers of stone and steel, humanity is engaged in a strange and audacious project. The attempt to measure time with such precision that it nearly stops changing at all. It is a pursuit born not from curiosity alone, but from an ancient impulse. The desire to pin down the one thing that seems forever beyond our grasp. We cannot slow time's flow, and we cannot reverse it. But perhaps, through the tools of science, we can trap it. Slice it into finer and finer intervals, and hold it still long enough to understand the universe itself. This is the ambition behind the most advanced timekeeping devices ever built. Atomic clocks and their even more refined successors. Optical lattice clocks, machines so precise that they lose less than a second over billions of years. Machines that serve as humanity's closest approximation to eternity. The idea of measuring time by the vibrations of atoms emerged in the mid-20th century. As physicists sought a standard, it's more stable and universal than the rotation of the Earth or the orbit of the Moon. The first cesium atomic clock, built in 1955 by Louis Essen and Jack Perry at the National Physical Laboratory in Teddington, England, was a milestone in that quest. Instead of relying on celestial motions, it measured the natural oscillations of cesium-133 atoms specifically, the frequency at which they switched between two energy states. This frequency, 9,192,631,770 cycles per second, became the definition of the second itself in 1967, replacing all older astronomical definitions. The change was more than a technical adjustment. It was a fundamental shift in humanity's relationship with time. No longer did our seconds depend on the spinning of a planet that wobbled and slowed over millennia. They were now anchored in the immutable rhythms of the atomic world, where time ticked with a steadiness that nothing in the heavens could match. Since then, atomic clocks have grown exponentially more precise. Today's most advanced versions, housed in underground facilities like the National Institute of Standards and Technology, NIST, in Boulder, Colorado, or the Physikalische Technische Bundesanstalt in Germany, are so stable that they would drift by less than 1 second over the entire 13.8 billion year history of the universe. These clocks are shielded from temperature fluctuations, isolated from seismic tremors, and protected from magnetic interference, all so that the atoms inside can vibrate undisturbed. Their tick is no longer a mechanical click or a swinging pendulum, but the whisper of nature itself, the faint, regular pulse of the quantum world. Yet even the cesium clock, once the pinnacle of precision, has been surpassed. In the 21st century, scientists have developed optical lattice clocks, which measure time using the much faster oscillations of light rather than the slower microwaves used in traditional atomic clocks. By trapping thousands of atoms, often strontium or ytterbium, in a lattice of laser light and measuring their transitions with extraordinary precision, these devices achieve accuracies hundreds of times greater than their predecessors. In 2015, researchers at GILA, a joint institute of NIST and the University of Colorado, built an optical lattice clock so stable that it would not gain or lose a second for 15 billion years. These machines are sensitive enough to detect tiny variations in gravities. Pull clocks placed just a centimeter apart on a laboratory table can tick at slightly different rates due to the curvature of space-time, predicted by Einstein's general relativity. This astonishing sensitivity is not just a scientific curiosity. It is a tool with profound implications. Ultra-precise clocks are essential for technologies that underpin modern life, from GPS navigation to telecommunications. Global positioning satellites, for instance, must account for time dilation caused by their speed and altitude relative to Earth. Without atomic clocks on board, their calculations would drift, rendering navigation useless. Future missions to explore the solar system, perhaps one day navigate the stars, will rely on even more accurate timekeeping. NASA and the European Space Agency envisioned spacecraft equipped with optical clocks that could navigate autonomously. using precise measurements of time to determine their position without relying on signals from Earth. In fundamental physics, these clocks could detect minute changes in the fundamental constants of nature or even test whether time itself flows at the same rate in all corners of the universe. But beyond their practical uses, these machines represent something deeper, an attempt to touch the untouchable, to tame a phenomenon that has always slipped through our fingers. Even the most precise clock does not stop time, nor does it reveal its ultimate nature. It can only measure the intervals between events with ever finer granularity, slicing the river of time into droplets so small that they seem almost motionless. In doing so, we approach a strange philosophical frontier. If time can be measured so precisely that its flow becomes imperceptible, does that bring us closer to understanding what it is? Or only to realizing that it is something we can never fully grasp? There is an irony in this pursuit. The more precisely we measure time, the more it escapes us. A clock that loses a second in 15 billion years reminds us not of our mastery over time, but of our place within it, brief, fleeting, and fragile. These deep time machines, buried beneath mountains and humming silently in their shielded chambers, are monuments to humanity's refusal to accept ignorance. They are our attempt to anchor ourselves in a universe that does not pause, to find certainty in a continuum that never repeats. And yet, their true power may lie not in their ability to count the seconds, but in the way they force us to confront the mystery of those seconds, to recognize that behind every tick lies something far more profound than measurement, something that no instrument, no matter how precise, will ever fully capture. In chasing the perfect clock, we are chasing the essence of time itself, and in that chase, we come closer to understanding not just the universe, but our own place within it. For most of human history, time was something measured by shadows on a wall, the passing of seasons, or the steady swing of a clock's pendulum. It was external and predictable, a force that flowed forward whether anyone was watching or not. But beneath that steady march lies another kind of time, one that is deeply personal, invisible to instruments, and shaped not by physics, but by memory, emotion, and the strange workings of the human mind. It is the time that seems to race during moments of terror, too slow to a crawl in the midst of wonder, and to disappear altogether in the rhythms of daily life. It is the reason childhood summers seem endless while adult years vanish in a blur. And it is a reminder that while the universe keeps time with the cold precision of atomic oscillations and planetary orbits, our minds experience it as something far more fluid and elusive. One of the most striking demonstrations of this difference comes from psychological experiments designed to study how extreme experiences distort our perception of time. In the early 2000s, cognitive scientist David Eagleman conducted a now famous experiment in which volunteers were dropped backward from a tower 45 meters high into a safety net. The fall lasted only about 2.5 seconds, yet when asked afterward, participants consistently reported that it seemed much longer. Some estimated it at 5 or 6 seconds. Eagleman proposed that this was not because their internal clocks had actually sped up, but because their brains, flooded with adrenaline, recorded far more information per unit of time during the fall than they normally would. When the memory was played back, it contained so much detail that the moment felt longer in retrospect. This phenomenon, sometimes called time dilation in psychology, though unrelated to the relativistic version in physics, is why moments of fear or crisis often feel stretched, as if time itself has slowed to allow us to react. The opposite effect is just as common, and perhaps even more haunting. Anyone who has felt a car accident unfold in slow motion knows that seconds can expand when the stakes are high, but ours can also evaporate when the mind is deeply engaged. Psychologists refer to this state as flow, a term popularized by Mihaly Csikszentmihalyi, in which a person becomes so absorbed in an activity, painting, writing, playing music, even solving a complex problem, that the sense of time's passage almost disappears. It is as if the mind, fully immersed in the present moment, ceases to track the passing of seconds and minutes altogether. In this way, time is not a constant backdrop, but a construct the mind builds and can abandon when attention is completely consumed. Age itself also plays a powerful role in shaping our experience of time, and it does so in ways that are both psychological and mathematical. Children often feel that days and summers stretch endlessly, while adults complain that the years vanish before they can grasp them. Part of this is proportional. For a 5-year-old, a single year represents 20% of their entire life, while for a 50-year-old it is only 2%. But there is more to it than arithmetic. Neurological studies suggest that novelty, the experience of encountering new sights, sounds, and challenges, causes the brain to create richer, denser memories, which in turn make periods of time feel longer in retrospect. Childhood is saturated with novelty. Every experience is new, every lesson a discovery. Adulthood, by contrast, often becomes routine. And with fewer distinct memories to anchor our perception, entire months and years can seem to slip by unnoticed. It is not that time accelerates as we age, but that our minds stop marking its passage as vividly. Trauma, too, can warp time in profound ways. Survivors of disasters, assaults, or wars often report moments that seemed frozen, where seconds stretched into what felt like hours. In some cases, the memory of the event remains outside normal time altogether, playing with vivid clarity years or decades later as though it were still unfolding. Neuroscientists believe this may be linked to the amygdala, the brain's center for fear and emotional processing, which can heighten awareness and alter memory formation during moments of extreme stress. In this heightened state, time is no longer linear. It becomes fragmented, looping back on itself as the mind struggles to process what has happened. Even awe, the deep, often overwhelming emotion inspired by vast landscapes, great works of art, or profound realizations can distort our sense of time. Psychologists Dr. Keltner and Jonathan Haidt, in their research on awe, found that people who experience it often report a feeling that time has slowed or even paused. This seems to happen because awe shifts our attention outward, away from ourselves and towards something larger, disrupting the internal mechanisms we use to track time. The sensation is fleeting, but it leaves a lasting impression, a reminder that time is not merely measured but felt. All of this points to a profound truth. The mind's time and the universe's time are rarely in perfect alignment. A second measured by an atomic clock is always the same, whether it ticks away in a laboratory or on a mountaintop. But a second lived can stretch into an eternity or vanish in an instant. Our internal clocks are malleable, shaped by attention, emotion, memory, and experience. And this flexibility has deep consequences for how we live our lives. It explains why we chase new experiences, travel, adventure, love, to slow the rush of years, and why we dread routines that compress our days into indistinguishable sameness. It is why moments of terror and wonder stay etched in memory long after they have passed. While thousands of ordinary hours fade into a blur, perhaps this is why the human relationship with time will always be uneasy. Physics offers us a universe where time is absolute in its precision, where each second is identical to the last. Psychology offers us a different truth, one where time bends and stretches according to the landscapes of our minds. And in the space between those two realities lies the human experience, a life measured not just by clocks and calendars, but by how deeply we feel each passing moment, by the memories that linger and the ones that slip away. The universe may not care whether a second feels long or short, but for us, that difference is the very essence of what it means to live within time. For more than a century, Einstein's theories of relativity have shaped our understanding of time as a flexible dimension, woven into the fabric of the universe, bending and stretching with motion and gravity, inseparable from the three dimensions of space. It was a revolution that shattered centuries of certainty, showing that time was not an independent backdrop against which events unfolded, but an integral part of the cosmic stage itself. Yet even this breakthrough, as profound as it was, may not be the final word. At the cutting edge of physics in the search for a deeper theory that unites relativity with quantum mechanics, in the attempts to understand what space and time truly are, a more unsettling idea is beginning to emerge. It is the notion that time, far from being fundamental, might be an illusion, a property that arises from something deeper and more basic, or perhaps something that does not exist at all. The challenge arises from one of the great, unsolved problems in science, the incompatibility of general relativity, which describes the large-scale structure of space and time with quantum mechanics, which governs the behavior of particles at the smallest scales. Each theory works beautifully in its own domain, yet when physicists try to merge them into a single framework, a theory of quantum gravity, the mathematics breaks down. Space and time, which are smooth and continuous in Einstein's equations, become jagged and undefined at the Planck scale, about y-35 meters, where quantum effects dominate. In this regime, time as we know it seems to dissolve. Equations that are supposed to describe the universe stop including time as a variable. Instead of a universe evolving from past to future, they describe a static, timeless reality, a block, where everything simply is. One of the most striking examples of this comes from the Wheeler-DeWitt equation, a central equation in some approaches to quantum gravity, formulated by John Wheeler and Bryce DeWitt in the 1960s. Unlike the familiar Schrödinger equation of quantum mechanics, which includes time as a parameter governing how systems evolve, the Wheeler-DeWitt equation does not contain time at all. It describes the quantum state of the entire universe, the wave function of the universe, as something unchanging. To many physicists, this is deeply unsettling because it seems to suggest that the passage of time is not fundamental, but an emergent feature of how we, as observers, experience the universe. In other words, time may not be a property of the cosmos itself, a byproduct of our interaction with it. Other approaches to quantum gravity reach similar conclusions. Loop quantum gravity, developed by physicists such as Carlo Rovelli and Lee Smolin beginning in the 1980s, attempts to quantize space itself, describing it not as a smooth continuum, but as a network of tiny, discrete loops woven together like a cosmic fabric. In this framework, space is granular, and time does not appear as an independent dimension. Instead, time emerges from the changing relationships between these loops. Much as temperature emerges from the motion of atoms but does not exist in a single atom itself. Rovelli has argued that the flow of time might be nothing more than a useful approximation, a macroscopic illusion that arises from deeper. We do not live inside time, he writes, we live inside change. If this is true, the implications are staggering. The idea that time might not exist as a fundamental feature of reality undermines our most basic notions of causality. The idea that one event leads to another, that the past produces the present, and the present shapes the future. In a timeless universe, there is no before or after in any absolute sense. Only a web of relationships that we interpret as sequences because of how we perceive change. Memory, too, becomes a puzzle. We think of memory as a record of the past, evidence that one moment followed another. But if the universe is fundamentally timeless, then memory itself may not be a window into a vanished past, but simply part of the present configuration of the universe. No more or less real than anything else. This view also forces us to reconsider the meaning we attach to existence. Our lives, our histories, even the story of the universe itself, are built on the assumption of a flow from beginning to end, from origin to outcome. Cosmology, for instance, speaks of the Big Bang as the moment when time began, but if time is emergent rather than fundamental, that language may be misleading. The Big Bang might not have been a moment at all, but rather a transition between different states of a timeless reality. In such a picture, the universe does not evolve. It simply is, in all its configurations, timelessly complete. What we experience as the unfolding of time may be no different from how a traveler experiences a landscape, moving through it but not causing it to grow or change. And yet, even if time is not fundamental, it is hard to deny its reality in our everyday lives. Our hearts beat, seasons change, memories accumulate, and plans are made. This is the paradox at the heart of modern physics. Time may be an illusion, but it is a necessary one, woven into the very structure of how we understand the world. It may emerge from deeper laws we do not yet comprehend, just as pressure and temperature emerge from the collective behavior of molecules, but it remains indispensable for describing experience. Perhaps the answer lies not in abolishing time from our worldview, but in accepting its layered nature. It's fundamental at some levels of description, emergent at others. If the universe truly has no before, time is not a river flowing from past to future, but a dimensionless structure in which everything simply exists. Then our notions of causality, memory, and meaning must change as well. The future may not come into being, and the past may never truly vanish. Everything, every event, every life, every moment, may be part of a timeless whole. It is a vision that defies intuition, that challenges the deepest habits of thought. But it is also one that hints at a profound truth: time, the very thing we believe defines our existence, may not be the foundation of reality at all. Instead, it may be the shadow cast by something deeper, a clue that points beyond the limits of human understanding, to a cosmos where before and after are not fundamental truths, but human inventions. Born of perception and destined, perhaps, to one day dissolve, for all the centuries humans have studied the stars, traced the movements of galaxies, and built models of the cosmos. There remains one question so vast and unsettling that even the most advanced equations tremble before it. How does the universe end? Every second that passes brings us closer to an answer. Yet that answer may be so distant in the future, trillions or quadrillions of years from now, that it hardly seems real. And yet, if we follow the logic of physics to its conclusions, the cosmos is not infinite in its story. It has a past, a present, and almost certainly a future. A final chapter that will unfold on a scale so immense that human language can barely grasp it. What makes this final chapter even more profound is that in many of the scenarios physicists now consider most likely, the end of the universe will also mean the end of time, or at least the end of time as we understand it. One of the most widely accepted models of the universe's future is known as heat death, a concept rooted in the second law of thermodynamics and first proposed by physicists like Lord Kelvin and Hermann von Helmholtz in the 19th century. It begins with a simple principle: over time, energy tends to spread out, entropy tends to increase, and differences in temperature and energy distribution, the very differences that allow stars to shine, planets to form, and life to exist, gradually diminish. As the universe expands and ages, stars will burn through their fuel and die. Galaxies will exhaust their gas and stop forming new stars. White dwarfs will cool into black dwarfs, neutron stars will fade into darkness, and even black holes will slowly evaporate through Hawking radiation, a process that could take 10,100 years or more. In this distant future, the universe will be cold, dark, and nearly uniform. A thin mist of particles and low-energy radiation spread across an ever-expanding void. With no gradients left to drive change, no stars to measure days or years, no processes to mark the passage of events, time will lose its meaning. It will not stop in a sudden moment. It will simply become irrelevant, because nothing will happen anymore. Yet heat death is only one possible fate. Another scenario, known as the Big Crunch, envisions a very different end. For decades, cosmologists debated whether the gravitational pull of all the matter in the universe might eventually halt its expansion and reverse it, causing galaxies to draw back together and the cosmos to collapse into a dense, hot state, perhaps even triggering another Big Bang. This idea was especially popular before the discovery, in 1998, that the universe's expansion is accelerating, driven by a mysterious force called dark energy. If dark energy were to weaken or reverse over time, a big crunch could still occur, collapsing space-time itself and bringing time to a fiery end. In such a scenario, the arrow of time would point inward rather than outward, and the final second would look much like the first, a moment of unimaginable density and heat where all of history is crushed into a single point. The opposite of the Big Crunch is the Big Rip, a model proposed by physicists Robert Caldwell, Mark Kamionkowski, and Nevin Weinberg in 2003. In this scenario, dark energy does not weaken, it grows stronger. If its repulsive force increases faster than the pull of gravity, it could eventually overwhelm every structure in the universe. Galaxies would tear apart, then solar systems, then planets, then molecules, and finally, even atoms themselves would be ripped to pieces. According to some calculations, this could happen tens of billions of years from now. The final second of the universe in this case would be a literal tearing of space-time. A catastrophic unraveling of reality itself. Time would not fade gently as it does in heat death, nor would it collapse inward as in a big crunch. It would shatter. These scenarios may seem impossibly distant, but they force physicists to confront a deeper question. If the universe has an end, does time itself end with it? In a heat-death scenario, time continues indefinitely. But without events or change, it becomes meaningless, an endless succession of empty moments with nothing to mark their passage. In a big crunch, time may truly stop, just as it may have begun at the Big Bang, because space-time itself would cease to exist. In a big rip, the very fabric of time would disintegrate. Each possibility offers a different answer to the question of what the last second. This means whether it is a literal final tick or an asymptotic fading. A moment that never truly arrives because it stretches into eternity. Philosophers and physicists alike wrestle with the implications of this. If time ends, does causality end with it? If there is no after, can there truly be a before? What does memory mean when the future ceases to exist? Even language begins to break down in the face of these questions. Because our very concepts of meaning and existence are bound to time. We speak of beginnings and endings, of causes and effects. But those ideas may be nothing more than artifacts of a universe still alive with change. When change itself dies, those ideas may die too, and yet paradoxically, the final moments of the universe may last forever, or at least feel like forever from within. In a universe approaching heat death, for instance, time stretches unimaginably, measured not in years or centuries, but in powers of 10 that defy comprehension. Processes that take longer than the age of the universe today will still unfold. Black holes will evaporate, protons may decay, and new forms of physics may emerge in the emptiness. Even the last second might not be a second at all, but an eternity of stillness, a state that is final yet unending. In contemplating the fate of the cosmos, we are forced to confront not only the limits of physics, but the limits of thought itself. The end of the universe is not a distant fireworks display we can watch from afar. It is the dissolution of the very stage upon which everything happens, the silence after the final note. Whether time fades into irrelevance, collapses into a singularity, or tears itself apart, one truth remains. The universe is a story with a last page. And even if that page takes trillions of years to turn, its inevitability gives every second before it, including this one, a weight it would not otherwise have. Every human life is lived entirely in the present, and yet the present is the one place we can never truly hold. It slips from our grasp the instant we reach for it, dissolving into memory even as we try to name it. By the time we say the word now, it is already gone. This strange and fundamental paradox has haunted thinkers for as long as people have tried to understand time. Philosophers, poets, and physicists alike have circled around this elusive point, searching for a way to define what the present truly is, and yet it continues to evade precise description. It is the horizon of experience, the thin edge where the past fades and the future begins. And it moves relentlessly forward, whether we want it to or not. For the ancient Greek philosopher Heraclitus, writing around 500 BC, the present was a river that could never be stepped into twice, because both the river and the person stepping into it were always changing. Time, in his view, was a continuous flow, and the present existed only as a fleeting moment within it, gone as soon as it arrived. Centuries later, Augustine of Hippo wrestled with the same paradox in his Confessions. Written around 400 CE, what then is time? He asked, if no one asks me, I know. If I wish to explain it to him who asks, I know not. Augustine proposed that the past exists only as memory, the future only as expectation, and the present itself is so thin that it seems to have no duration at all. And yet, he concluded, it is within this evanescent present that we live, think, and act. Without it, the past and future would be meaningless abstractions. Modern physics has only deepened the mystery rather than solved it. In Einstein's theory of relativity, the present is not a universal concept. Two observers moving at different speeds, or in different gravitational fields, will disagree about which events are happening. Now, what we call the present is not an absolute slice of the universe, but a perspective, a feature of our own motion and position in space-time. Even more unsettling is the implication of the block universe view, which arises naturally from relativity's equations. All moments past, present, and future exist simultaneously within the four-dimensional fabric of space-time. The present, in this view, is not something that moves. It is simply the point in the block where our consciousness happens to be located. We do not pass through time. We are embedded in it. Yet, despite these scientific insights, the feeling of the present remains one of the most immediate and powerful aspects of human experience. It is where we feel joy or grief, where we make choices, where we love, lose, and remember. The present is the only place where we can act. The past is unchangeable, future unknowable, and yet it is also the most fragile thing we know. Neuroscientists have shown that even our perception of now is not instantaneous, but constructed. It takes about 80 milliseconds for the brain to process sensory information, which means that what we experience as the present is already slightly in the past. The now we feel is a reconstruction stitched together by the mind to create the illusion of continuity. Without this subtle delay, our experience of the world would be disjointed and chaotic. A jumble of unconnected moments rather than a flowing stream. This illusion is not a flaw but a necessity. The sense of a moving present allows us to build narratives, to understand cause and effect, to make plans, to imagine futures and recall pasts. Without it, language, memory, and meaning itself might collapse. Poets have long intuited this connection between time and storytelling. T.S. Eliot, in 4 quartets, wrote of the still point of the turning world, a moment that contains all moments, suggesting that the present is not merely a point in time, but the convergence of everything that has been and everything that will be. Physicist Carlo Rovelli has echoed this sentiment in a different language, arguing that time is not a fundamental feature of reality, but a convenient way of organizing our experience of change. We inhabit time as fish inhabit water, he writes. Yet we may be wrong to think that water is the structure of reality itself. The more we learn, the more it seems that time, and especially the present, is less a thing and more a relationship. A story we tell ourselves to make sense of motion and transformation. The ticking of a clock, the swing of a pendulum, the decay of a radioactive atom. These are not time itself, but changes we measure and name. And the now is simply the point where our awareness meets those changes. It is not a fixed coordinate, but a moving boundary, a line drawn by consciousness across the unfolding of events. Even our language betrays this. We speak of holding on to the present, living in the moment, losing track of time, all metaphors that admit our inability to stop it. What would it mean if time were not a fundamental part of the universe at all, but simply the scaffolding we build around change? It would mean that the present is not a cosmic feature, but a cognitive one, born from the way our minds interact with reality. It would mean that past and future are not destinations we travel to, but perspectives we construct. And it would mean that the now, the fleeting, precious, irretrievable now, is both everything we have and something that never truly exists. And perhaps that is the final lesson time has to offer. The present, which we chase and name and try to hold still, is never really there. It is always slipping forward, always vanishing, always just beyond our reach. Yet in that vanishing lies the essence of what it means to be alive, not to grasp the moment, but to move with it. To live in the story it allows us to tell. We cannot freeze the now any more than we can stop the tide from rising, but we can stand within its flow, aware that even as it disappears, it is the only place we have ever been. And in that awareness, fleeting as it is, time becomes not a prison, but a companion, a story we tell, a mirror of change, a reminder that to exist at all is to exist in a moment that is already gone.